type questions. Okay, so this one in red is me, and in blue is a student. So it says that I have a head start of 30 meters. I accelerate at a half a meter per second squared, and I have an initial velocity of 6 meters per second. So up here, this is the equation. And I went t greater than 0 because that's just going to be the domain. So again, started at 30, running at 6 meters per second at the start, and then I accelerated at a half. So again, this 1/2 at squared term, if I accelerate at a half, then that coefficient there will actually just be a quarter. Okay, so that represents me. I'm in the red, right? Starting at 0, and I move along. A student has a 2 meters per second initial velocity, accelerates at 1 meter per second squared, and starts at the origin. So this would be the student's position equation, right? No initial start, 2 is the velocity, and a 1 meter per second acceleration would have a half there. Okay, so the question might be, when does the student eventually catch me? Again, look at the student, it's behind, but he or she's going to accelerate, and boom. At 21.565 seconds, we're going to be at the same location. We're going to be 275 meters away from the origin. Again, I got a 30 meter head start, so I didn't actually run 275, but we are located at 275 meters at 21.565 seconds. Okay? So that's certainly something we could ask. I could ask how fast people are going. Well, think about, take the derivative of this equation, and you get the velocity equation, right? V equals V naught plus AT, right? So I could graph that. That's my velocity. And I could look at the velocity of the student. Started at 2, and then was accelerating at 1. And then you could find our speed at any moment by looking at the y values on this particular graph. Okay? If you look at me, positive velocity, positive acceleration, that's speeding up. Same thing with the student in this case. Positive velocity to start, positive acceleration, speeding up. Look at the curvature. I'm getting steeper and steeper and steeper. When these signs agree, in this case they're both positive for me and both positive for the student, that means the velocity is positive, and the definition of positive acceleration is increasing velocity. Okay, so these are both speeding up scenarios. Okay, let's go to a purple train and an orange train. Okay, so the purple train starts at the origin, has an initial velocity of 5, and is speeding up at 4 meters per second squared, right? That's me giving you the acceleration rate. And in this case, since I'm speeding up and I was initially moving to the right, both of these should be positive. Positive for a velocity, positive acceleration. Now again, the acceleration is 4, so it's 1/2 times 4 times t squared, so that's just a 2. The orange train starts 30 meters to the right, but it's moving left at 4 meters per second, but I do say it's speeding up at 2 meters per second squared. Think about that one. If it's speeding up, that means it's actually accelerating to the left. So 30 is the starting position. I'm moving left initially, so my V naught is -4, and then if I wanted to speed up, I got to put a minus sign there for the acceleration. The acceleration is negative, which means a decrease of velocity, but since velocity is -4, decreasing that will make that bigger, which will speed me up. If you look at the velocity equations for both of them, V equals 5 plus 4t, right? See how I'm speeding up? That positive acceleration will make the 5 bigger. And down here, the velocity for the orange train is -4 minus 2t. Again, subtracting from a negative will in fact make that speeding up. Okay, so if you wanted to know where they hit, we can look at the intersection of the two graphs. Okay, so after 2 seconds, they're both at a location of 18 meters from the right of the origin. Again, the purple train is starting at the origin. The orange train starts 30 meters to the right. They meet at 2,18. If you want to know how fast they are moving, you could just plug 2 into here. So the purple train is moving at 13, and the orange train will be moving at -8. You could figure out where they're located at any moment. You could figure out how fast they were going at any moment. Again, writing the equations for their position and their velocity is pretty important. Okay, makes sense? So we can do plus and plus and get speeding up. We can do minus and minus. It's just speeding up in the other direction. This one, when we were both just running both in the same direction and both speeding up, well, then everything was kind of positive. Okay, so now let's look at the difference in the question we did in class. In the class, the red train was moving 20 meters per second, but it was slowing down. Oh, I don't know why that's there. Slowing down, and it started at the origin. Okay, so it was moving to the right at 20, and it was slowing down at 1. And again, I didn't actually simplify here, so this is the minus 1/2 AT squared. It's a minus when this is a plus. This is a slowdown, moving to the right, but slowing down, positive and then negative. Okay, now this one doesn't have that acceleration forever. And it could, but in this case, it doesn't. It's just hitting the brakes. So once it stops, the story is actually over. So this graph really shouldn't be what it is. It really should be this graph. And now see how it stops. And to make it even better, watch this. I'll make it, boom. Now I'm actually going to stand there for more time. So I'm going to move to the right, slow down at that moment right there, at 20, I am actually stopped because that's how long it took. Now remember, look, it's pretty easy. 20 meters per second, and you're going to slow down 1 meter per second every second. It's going to take 20 seconds. And I can figure out where I'm located at 20 seconds, and then I can just stay there forever. I could even make that, make it 100 seconds. So I'm standing there forever, okay? Now, look at the blue train. The blue train was moving left at 40 meters per second. It was also slowing down at 1 meter per second squared, but it starts at 950 meters to the right of the red train. Again, it tells you that the two trains are 950 meters apart. So then the blue equation represents the blue train. 950 starting position minus 40t has a negative 40 velocity, right? You're moving to the left. And look, it's slowing down. So I made these two signs opposite. If the velocity is negative and the acceleration in term is positive, that will make it slow down. Okay, so this one, if you look at the blue, you're asking yourself, when does the blue intersect the red? And look, right there, those two trains are at the same location at the same time. And really, we'll put a domain restriction on that, and now we have everything we want. Put that at 30, and boom. That right there is when the two trains hit. The red train slows down and stops. The blue train starts at 950, moves to the left, but is slowing down, but it is still moving when it hits the red train. So at 30 seconds, they hit at exactly 200 meters. Now, if the red train didn't stop, well, then it would have been more like this. It would have been just the intersection, and they both were moving at that point. But in this one, the red train slowed down at a rate that it actually stopped before the blue train ever hit it. However, in all three cases, it really is the intersection of the curves. It's just that this one is a little more difficult because you have to realize that the red train actually stops. Because if you don't make it ever stop and you just graph them like this, you might think that the curves never hit each other. But this part of the red curve is nonsense because it doesn't actually keep doing that acceleration rate. It doesn't keep accelerating at -1. It only accelerates to the point where it stops. So that's really the red curve. This blue curve also, once the crash happens, then the story's over. And so really, this is also simply the blue curve, and that is the intersection of those two things. Okay, and then once you know the time, you can find the velocity. Again, you can take the derivatives of this to find the velocity functions. You can figure out how far each train traveled and all that stuff. But again, writing the position equation with initial position, initial velocity, and acceleration is key to solving both the red and blue train question. In this case, the purple and orange question where they are going to both be moving when they hit. Or if you have a situation where you're running in the same direction as someone else. The person ahead might be moving faster at the beginning, but his acceleration probably isn't as good. Where this person is moving slower at the beginning, but is accelerating at a bigger rate, and eventually they're going to catch and go. And there's that coordinate. And you can do all of this on your graphing calculator. I hope this kind of helps you get the idea of how to write position functions and velocity functions, and then also how to use them in stories.